It's a pleasure for me to introduce the first speaker of today, and that will be Dr. Dennis Christensen. Dennis is a fellow adjuvant researcher that has a very impressive track record in developing adjuvants, namely the CAF series, which you may have heard of, that were developed at this Statens Serum Institute and are now being developed as commercial products by Croda Pharma. Dennis will share with us some research insights about the Adjuvant series and share his experiences on his career path, which he is currently at as Global Head of Research and Development for Adjuvant Systems at Croda. Please take it away, Dennis.
Yes, can you see my screen now?
Yes.
Good. So thank you very much for the introduction. Just to mention to begin with that I have a dual role, a dual position, you could say. It's true that I'm head of global R&D for vaccine adjuvant systems at Croda Pharma. I'll come back to that in a minute. And then I also have an adjunct research professorship at Statens Serum Institute. But first, let's see if I can get this to work. So I was told that I should come with an introduction to my career, and I didn't really have a slide on that, so I had to invent that. And I thought, well, where did I start? And I think we all had dreams when we were kids. I think we can all remember that. You know, I had, of course, everybody had dreamed about working in a candy factory when they were 4 years old, I think. But I had many different dreams, and it was actually not until I ended up in high school that my track was beginning to settle. I ended up by coincidence at the technical high school in Denmark, having a teacher who told me what I should do. Sometimes it's really nice to meet people that tell you, I think you should do this, because we have so many options. We had many options when I started my career, but I think today you probably have even more in your career development. There are so many decisions to be taken. So sometimes it's nice to have people telling you what to do. So that nice teacher told me that I should study pharmacy. In the interim, I had a lot of other crazy dreams, like being a globetrotter. That was when I was backpacking. I saw myself as Michael Palin, the future of Michael Palin, and so on. Of course, that they were temporary dreams, not very realistic. But then I started university in Copenhagen, and with the focus on of course on medicine, on pharmacy. It's a very scientific driven university direction in Denmark compared to many other places. It's not very focused on primary practice of pharmacy, and I really enjoyed the lab work. So I started, in the end of the university time, I started looking around what could I do to continue that. I had a lot of options to do my master thesis in different places, but ended up writing to Statens Serum Institute and say, hey, could you use someone like with my profile? Because I think it's really interesting what you do, and you make a difference. I went to an interview and got a master project there, and were later offered a PhD studentship. And then I stayed there for 18 years, with roughly 10 months in total on paternity leave. Definitely something I can recommend. But I stayed there for many years, and in the end also driving the vaccine adjuvant research there with the CAF adjuvants. Without having, and that was what I realized when I did this slide, without actually having any dreams. I was just going with the flow, offering new challenges, and maybe, you know, not reflecting much. I was just happy about what I was doing. I didn't have to take any decisions. But I also felt in the end, or the last years, a bit of frustration that I had developed all these or had been part of developing all these fantastic technologies. And what I saw was wrong in the adjuvant field, or was missing in the adjuvant field, were a company that could lift it into commercial scales, those that could dare and actually could manage to take it from bench to bed, or from at least from phase 1 GMP production into commercial scale. And that was when I stumbled into Croda, that had acquired Biosector from Brenntag, the biggest producer of aluminum adjuvants, and had acquired Avanti Polar Lipids, a big toolbox. It's like that's the candy store of a scientist like me, with a lot of interesting compositions, components, excipients that you can build into different adjuvant systems, and they were kind of trying to put together a strategy for the adjuvant, for the next generation adjuvant business, and asked me whether I was interested in doing that. And of course, I was really interested. I have now spent 3 years there building up the R&D in that area, with a much more commercial, much more strategic commercial angle to it. Also realizing that I really missed the scientific discussions on the immunological level, on the more really down to earth science, and then I got the opportunity to, in addition to continue this, as I see, very important role of getting Croda established to be a supplier of these fantastic adjuvants that are invented by many different scientists over the world, to also have, you could say, one foot into continuing into the academic world by getting an adjunct professorship at SSI. And that's where I am today. So both working in academia and industry together is it's interesting, it's challenging, and it's definitely showing that how different these two worlds are, but also that there are a lot of synergies that can be used. I think that's enough for me in this part, but I'll try to bring it into the story, some of my career developments. But what we are going into is, of course, telling a little more about what vaccine adjuvants, delivery systems, and immune modulators are, where how that has evolved over the years that I have been in the field, and also where I see it's going. So first of all, as I said, I'm a pharmacist of background, and we tend to put things into boxes and try to structure really much. And I don't see vaccines being that much different from any other medicine. So it's basically, if you can fulfill these 5 points in designing a vaccine, you have a pretty good vaccine. So presenting sufficient amount of the right antigen in the right conformation to the right cell population, supporting with the right co-stimuli for a sufficient amount of time, then you really have a good vaccine. Especially if you notice, actually point 3, 4, and 5 are all about delivery and stimulation, and that's where the adjuvant comes in. So actually the adjuvant plays a major role in modern vaccines. Compared to old technologies, which are based on wholly inactivated, attenuated bacteria or viruses, modern vaccines are typically subunit based, meaning that specific antigens have been selected and prepared recombinantly, or produced as RNA for our own cell machinery to produce the antigens. And no matter what, these RNA structures or proteins or peptides, or what technology you're basing them on, need an adjuvant. An adjuvant is simply just a helper system that can deliver your antigen and that can stimulate your immune system to recognize your your antigen. So if we boil it down, then a modern vaccine contains, of course, of the antigen. That's the one we will teach the immune system to recognize. That's the goal. That's the one that the T cells and the B cells should recognize when we get the infection. On top of that, that antigen needs a delivery system that can deliver the antigen to those cells that can facilitate the presentation of the antigen to those T and B cells. And on top of that, an immune modulator that shapes the immune fingerprint, that tells the immune system how to recognize that or how to react when they recognize that antigen. And so that's how modern vaccines are. But if we are stepping a little back and looking into where we were when I started at SSI in 2004, so more than 20 years ago, of course, we had the aluminum adjuvants. They were introduced in the early 1930s after Gaston Ramon in 1926 discovered that it was a quite potent immune potentiator for the production of anti-diphtheria toxins. He had the job to increase production of this anti-diphtheria antibody in horses. And he basically took whatever he had on the shelf, so a very empirical approach, you could say, to find something. He tested, as you can see on the presentation, basically everything, even what he had in the kitchen, and injected that into horses together with the diphtheria toxin to see what was best at inducing increased antibody responses. He had aluminum composition standing on the shelf because it was used as a preservative, and that worked very, very well. So he continued with that work, and it was expanded into other research groups. And then in the early 30s, it was introduced in the diphtheria vaccines. So a very, very fast development compared to what we can perform today. After that, nothing happened for more than 60 years until in the mid-90s, first the virosomes were introduced, and later on the squalene emulsion, the first one being the MF59 from Chiron Novartis. The virosomes were taken off market again, so there are no registered product on the market using virosomes today due to some serious adverse events that were discovered from this platform. MF59 have spun out to several different similars. I'll come back to that afterwards. But nothing happened those 60 years, but then with 2004, actually, with the first introduction, GSK came with the AS04, which is a combination of a TLR4 ligand MPL with L-hydrogel. And then came a number of different adjuvant systems, and especially the years around Corona, we saw an expansion of novel adjuvants coming in, not only for the Corona vaccines, I should say, but the Corona vaccines definitely grow at least 3 platforms into the market, including the RNA vaccines using LNPs as delivery systems and thus adjuvants. Matrix M came in the Novavax vaccine, so the ISCOMs were presented, and then we have this addition of what we call Alum Plus vaccines, where we combine CBG or TLR7/8 ligand, so I think it's resiquimod, with aluminum to shape the immunity of the aluminum adjuvants. But we can ask ourselves, why did nothing happen for so many years? From alum was introduced till the mid-90s. Well, the basic thing was, based on the immune system, we didn't know anything about it. Thymus function wasn't discovered until 1961. We had the Th1, Th2 differentiation in the mid-80s. And maybe more important for what you have seen introduced into the adjuvant systems, the whole TLR or the pattern recognition receptor families were not discovered until the mid-90s, and the role of TLR4 not published until 1998. So basically everything that happened before that in the design of adjuvants were based on empiric. From there on, and through the last 20 years, we have had a massive amount of new insight into how the innate immune system works. And that's what we are building our novel technologies on today. And that's really important. So with the modern vaccines, especially on the adjuvant design or the vaccine design, in order to present the vaccine to the immune system, we have moved from empiric into rational design, because we now today understand how the innate immune system works and how we can trigger it to react the way we want. That, of course, increases the safety profile, but it also increases our ability to refine and adjust the immune responses that comes out of it. And of course, that's important because there is no one solution fits all. We have learned that based on empiric. We have seen through history examples where induced immune responses actually made the susceptibility to the infection worse. We have seen that, for example, with the first RSV vaccines that were combined with aluminum adjuvants. Aluminum adjuvants drive a strong Th2 response, and we learned afterwards that RSV actually is good at hijacking, especially Th2 cells, and thereby actually making it difficult to fight the infection. So therefore, it's really important to find that immune fingerprint that is necessary to obtain resistance, to obtain protection against infection, rather than, of course, susceptibility. And part of that study of mapping out how different immune modulators reacted was what we did with the CAF adjuvant series, and are still continuing doing, because there will continuously be new immune modulators coming in. Where we basically combine the base platform, it's cationic liposomes, highly rigid liposomes, that where we can combine those with different types of immune modulators. Basically, the base of them also contain either TDB or MMG, which are both C-type lectin receptor agonists. So downstream, really good at signaling and maturing a Th17 response. And then combining those with different TLRs or other CLRs or other pattern recognition receptors agonists to shape and define different immune fingerprints. And that's what that's what the table kind of tries to illustrate, without making it too complicated. That we actually, with the family, and I should say, I think the total list has 50 plus or something now. But just to illustrate is that by combining different immune modulators to the base, we can actually shape the immunity to give different qualities. What we also learned, and you could say this, a lot of this was actually done in a period where we didn't know that much about how it worked. The understanding of the signaling in the innate immune system were not that matured in the early 2000s. So, but over the years, we learned a lot, and from the whole society generating an enormous amount of data that could then suddenly, where we could suddenly put that into context to what we were observing with our adjuvant systems, and realizing, why didn't this work perfectly by doing this or this? And we learned how to shape, and also realize that we also need to make sure to deliver the these immune modulators to the right cells, and maybe the way we designed our adjuvant systems, our delivery systems, were not the same way. Because the problem is the immune system is probably the most complicated organ in the body, and just as an example, dendritic cells are not just dendritic cells. They were pretty much when I started 25 years ago, or 21 years ago. There were a few subsets that were known, but actually today it's a plethora of maybe 50 plus different subsets of dendritic cells that each have different ways of reacting, different ways to be stimulated, different roles to play depending on where they're located. And their activation state and so on. We have some examples here from some very early examples that actually illustrate or that led to this understanding, because it was shown quite early that all these different TLRs, so toll-like receptors, they're not evenly distributed on different cells, which means that you need also, if you choose a TLR, we can, for example, take the TLR3 as an example, which we can see here. It's highly variable which dendritic cells there are presented on. So if you use TLR3 as an adjuvant, you also need to make sure that the vaccine reaches those cells that have TLR3 represented in their naive state. Otherwise, you won't have the same effect out of it. And that realization suddenly added the complexity of also looking into other delivery systems or other routes of administration that could facilitate this. The CAF09 system is a really good example of where we say, well, actually, if we give the CAF09, if I'm going back, the CAF09 system is the combination of poly-IC, so a TLR3 receptor with agonist with the CAF04 system, and well, if we just give that intramuscularly, we don't see much difference between CAF04 and CAF09B, simply because poly-IC do not meet the receptors, the TLR3 receptors, and in the intramuscular side. So, but if we use it intranasally, or we inject it interperitoneally or intradermally, where we reach the mucosal-like type tissues, where we have what we call cross priming dendritic cells in mouse, they're defined as these CD8 alpha positive or CD103 positive dendritic cells, then we suddenly get that effect of poly-IC. And that kind of illustrates the effect that we need to design our delivery system or our delivery of our vaccine to not only support the antigen, but also the immune stimulators. I have another small example, because of course, squalene emulsions, we have both, well, we have three registered products, or three different squalene emulsion adjuvants in registered products, all based on squalene emulsions. We have the MF59 as the one that has been used the most, and then the other big one is ASO3 from GSK. But they have a very specific mechanism of action that makes them pretty much opposite of what CAF01 does, and I'll try to illustrate that. So it's basically and that is partly due to the stimulation, but also due to the delivery system, because what the squalene emulsion does is that they don't interact with the antigen. Actually, the antigen is free flowing around. It should just be together with, co-administered with it. The mechanism is that it mediates a very fast delivery to the draining lymph nodes, where it then targets those dendritic cells there, medullary macrophages and B cells. On the other hand, the CAF01, when you inject it, where you inject it, it stays there. It forms a depot there. It binds the antigen quite strongly. So therefore, you also make sure that you create a depot of the antigen, where from dendritic cells and macrophages can come over time and chop up and eat it. So you have a prolonged presentation at the site of injection. Therefore, it targets the migratory dendritic cells and macrophages that will encapsulate that depot. And these are quite well described, but what consequence does that have then to the immune system? Well, first of all, since the squalene emulsions very fast deliver something to the draining lymph node, you have a very fast antibody response. You will have a very quick activation of B cells and medullary macrophages and FDCs, and therefore you see a very fast antibody response. You also see a strong antibody response with CAF, but since it's coming from the other side where you have a very slow, very prolonged presentation, it takes much longer time. Over time, responses will be similar or maybe in some cases even higher than with the squalene emulsions. And that might be due to the fact that with the squalene emulsions, we see very, very little T-cell responses. We do see it very early on in the draining lymph nodes, and that's because, well, the T cells are activated, but they are all dragged into the germinal centers, and therefore they don't get any. You don't generate any memory T cells, where the CAF system, because of the depot effect or the slow delivery, actually first mediate a T cell response, and then that T cell response can support the B cell responses. So you could say that the squalene emulsion, that's the B cell responses controlling the T cell responses. For the CAF system, it's the other way around. You can also see here, this is the pharmacokinetics of the two emulsions. And you can see that CAF1 and squalene emulsions have completely opposite kinetics, with draining, very fast draining to the lymph node of the squalene emulsions and hardly any draining, but high maintenance at the site of injection. That leads to germinal center formation. Kinetics are also different. You have a very fast germinal center kinetics for the squalene emulsions, much slower for the CAF adjuvants. That has a consequence for you when you compare those two, because if you can imagine from classical school book, you know that the most optimal time point to vaccinate and vaccinate on top of or boost a primed immune response is when the germinal centers have collapsed again. But in many cases, that's not what we do in animals. So you have to have that in mind, that you have to know the kinetics in order to boost correctly. I've tried to illustrate it in this figure, where you can see that we, in most cases, we actually boost for both squalene emulsions and the CAF1, we boost actually when we have an ongoing germinal center response. So you could call it a second priming. I came out with an opinion paper in Pharmaceutics last year on that, where I discussed that issue, whether we actually give the different vaccines the most optimal conditions when we compare them in vivo. So the take-home message from my side is where I see that we are moving much more into in the vaccine adjuvant field, is that we need to know much more about our which, where, and how. So which cells should we target to support the immune responses we want? We know much more today about that. Where are these cells located, and how should these cells take up the vaccine to get the most optimal immune responses on your design? Are you using protein antigens, or are you using mRNA? And of course, that depends on where in the cell it should end up. And from there, we should then rationally design our delivery system and combine with those immune stimulators that can support the immune response. So much more moving away from into the rational design of new adjuvants. Just quickly on your career advices, I was told that I was old enough to give some of those. One thing I've been happy about is that to follow my heart. You know, do what you find most appealing. You should feel like you want to go to work, not having to go to work. That's the most important thing, I would say. Make yourself indispensable. That's a really good thing, because then you can decide yourself whether you should stay or leave. Be focused on maintaining high quality. Otherwise, you won't be satisfied yourself. Make sure you expand your knowledge. A lot is happening in the field around you, no matter what research you do, and be on top of that can be difficult. It's good we have AI to help us today, so learn to use that if you don't know how. Don't be shy to present crazy ideas. These are the ones that change the world. Long working hours is not a measure of productivity. Remember your family and friends, and then don't rush. Many of you will be working until you're plus 70, so no need to be burned out 40-year-old CEO. And I think that was it for me.
Thank you so much, Dennis. Brilliant presentation. We already have 3 questions actually. So just as a reminder, if you have any question, you have a Q&A box on the bottom, so please don't hesitate to ask. So I will just take 2 for this moment. We have from Javed Hamed Nguyen. So how do different dendritic cell subset influence immune response via parallel recognition receptors such as TLR3, TLR7, and TLR9?
I would say there's not a one simple answer to that. We could talk for hours about that, but I think what is important is to look at their role at the site, because if you take, for example, I think depending on where they're located, actually the TLR will also downstream signal or end out having different support. Because it's not only the TLR signaling, but also the environment around it that facilitate that. But what is most crucial, I think, is that some dendritic cells do not, in the naive stage, have many of these receptors. You have you can especially see it if you go into and look at the representation of TLR7 and TLR3. They are often very opposite, and therefore, if in their naive state, not saying that they cannot present it, but typically, for example, the mentioned CD103 positive dendritic cells that have high expression in the naive state of the TLR3 do not present TLR7. And therefore you need to think about how to deliver to it. And then it's a question, those dendritic cells, let's say CD103 dendritic cells that you find in the skin, do react differently and do have different functions than those in the airways, for example, because they are affected by their environment. There are other cells around them that also help modulate their roles and responsibilities. In the gut, where we also have them, we have a very high regulatory environment, or in the intestines, we have in regulatory environment due to a high expression of TGF-beta. That affects how these dendritic cells react. In the airways, we don't have that, and they will react differently, even though they are, from naive state, basically the same cells. So it's not a simple answer. I think we need some case stories to do that. But it's something to be aware of, that you cannot just, say they're all the same.
Yeah, thank you very much. So yes, this answer took quite some time, was a difficult question. So maybe we switch directly to Nina, and then we come back with the Q&A with everyone after Nina's presentation.
Mm-hmm. Yeah, so if people still have questions, please put them in the Q&A box. Hopefully we have times for afterwards, or they can be maybe responded to by email or follow-up. So to transition into the early career researcher presentations of today, I have the pleasure to welcome Nina Nguyen, postdoc from also at the Statens and Serum Institute, who has a background both in vaccine research and immunology. And she will present her work on investigating chlamydia vaccine candidates with the CAF-1 adjuvant. So please take it away, Nina.
Yes, thank you. Oh, I need to share my screen. Oh, where is it? Sorry, I thought I had it ready.
And if you like, Dennis, you could also maybe write answers in the Q&A in the meantime, if you like.
Yes, okay, I think I got it now. Yes, do you see my screen? Okay, thank you for the nice introduction, Celine, and thank you for inviting me to talk and share my data for you guys. So I'm gonna talk more about how what kind of immune responses CAF-1 actually induce against an infection. So I'm gonna talk to you today about how vaccine-induced Th17 T cells contribute to protection against infection with Chlamydia trachomatis. I don't have a career slide for me, but I also started, like Dennis, as a master's student at the Statens Serum Institute just a few years after him, and have been here since 2018. And I did my PhD here and also continued as a postdoctoral researcher. So I'm just going to start out by giving you a quick introduction to what we do here. So I work at the Center for Vaccine Research at Statens Serum Institute, and what we do here is that we do translational research, and which cover everything from discovery in animal models to clinical trials in humans, clinical phase 1 and 2, and also market approval. And then we try to find partners to collaborate with and develop the vaccine even further. So that enables us to take the knowledge that we gain from the clinical trials and product development and feed into our discovery and make more exciting discoveries. So the projects that we have here at CVR, we have some more stable projects, then we have some partnering and contract projects. The projects that we do have here stably is the vaccines against tuberculosis and vaccines against chlamydia, which I'm going to talk more to you about. And then we have vaccine against gastrointestinal infection, as well as also adjuvant platform, where we investigate different novel adjuvant systems. So our niche in our institute is that we select vaccine targets that the industry does not focus on, and that can be because of business and also because of difficulty in developing these vaccine targets. So it covers poverty-related diseases such as TB, which have limited interest from the industry due to lack of business incentive. And then we also focus on difficult vaccine targets such as chlamydia, where the current knowledge do not support a streamlined development of a vaccine. So why are we interested in developing a vaccine against chlamydia? So chlamydia infection poses a public health issue around the world. It is caused by infection by this intracellular bacterium, Chlamydia trachomatis, and it gives rise to estimated 131 million incidences every year globally. And it causes these devastating diseases such as infertility, ectopic pregnancy, and also can cause trachoma, which leads to blindness. We do have a current treatment right now. It's antibiotic-based. However, because over half of the cases, people are asymptomatic, meaning that they're very difficult to diagnose. and therefore very difficult to treat with antibiotic. Also, we do not really develop any natural induced immunity after infection. So in many cases, we do have a lot of reinfection occurring, which increases the risk of developing the associated disease. So there is a global consensus that we need a vaccine that can prevent infection and disease. And to do that, we need to understand protective immune responses against chlamydia. So we have a current vaccine candidate, which has been through 2 phase 1 clinical trials. It's been shown to be safe and immunogenic in humans. It consists of CTH522, which is a recombinant fusion antigen, and it consists of a major membrane protein on chlamydia. And we have formulated together with CAF1. So together it gives a Th1 and Th17 immune response, and also many neutralizing antibodies. So we know in the chlamydia field that Th1 T cells are protective. However, the role of Th17 T cells is still being established and discussed. So a lot of previous research have shown that infection-induced Th17 T cells has shown to induce pathology. However, recent studies have shown that Th17 T cells might be involved in protection. So a study done by Rixon in 2022 showed that mice that lacked Th1 T cells had an immune response skewed towards Th17 T cells and were still able to clear infection without Th1. They later did a other study where they looked at mice deficient in Th17 T cells and showed that they had the delayed clearance. In support of this, another research group showed that chlamydia-exposed women who had a Th17 profile were associated with resistance towards infection, towards reinfection. So that highlights again that maybe Th17 T cells could play a role in protection against chlamydia. We also know that Th17 T cells are plastic and might contribute to protective immune responses by transdifferentiating into other effector T cells. So we have also shown that Th17 T cells correlate with protection. When we vaccinate mice and challenge them, we see that there's an early recruitment of Th17 T cells shown here. And they actually respond towards infection by expanding, and then they also retract, but they actually stay there as tissue-resident memory T cells in the tissue. Then we also see that when we vaccinate the mice, we see that the Th17 response correlate with a control of bacterial proliferation. They have protection against infection. And also, when we looked at the pathology development, we see a significantly less pathology development in the ones that were vaccinated. If we give them, in another study, we actually tested how this vaccine would work in a post-exposure setting, protecting individuals that have already been exposed to chlamydia. And we saw in animal models that the Th17 T cells also correlated with protection there and also reduced pathology. So we were really curious about investigating the role of Th17 T cells further. So our approach to investigating the role was to characterize these CAF1-induced Th17 T cells. And what we did was that we used this IL-17 fate reporter mice and fate map all the IL-17 positive cells. So we use this Cree-Log system, which permanently marks all cells with a history of IL-17 expression. So also the ones that have previously expressed IL-17 but do not anymore. So what we did is that we vaccinated the mice 3 times, and then we looked at the systemic immunity after vaccination. To look at the vaccine-specific CD4 T cells, we in vitro stimulated the cells with our vaccine antigen, and then looked at the cytokines that they produced. So the first figure here is that we see that we have our vaccinated group and a non-vaccinated group, and we looked at the YFP expression within the CD4 positive T cells in the blood. And we see here that there's the YFP expression is only present in the ones that were vaccinated. So the YFP positive CD4 T cells are only present after vaccination and not in naive mice. If we look further into the Th1 and Th17 response, I will just quickly explain my gating here. We looked at the Th1 T cells defined by IL-17 negative expression and expression of TNF-alpha, IL-2, and interferon gamma. And then we characterized Th17 T cells as the one that expressed cytokines and also expressed IL-17. If we look at those two populations, we actually see that, as expected, we expect that the Th17 T cells will express this yellow fluorescent protein, meaning that they are expressing IL-17. However, we also saw that there was a expression of YFP in the Th1 T cells, meaning that the Th17 T cells give rise to Th1 T cells after vaccination. So to look further, we looked what happened to this cell population after infection. Do they get recruited into the genital tract and respond towards infection? So we looked after infection from day 3 to day 57. So what we see here is the yellow line is the yellow fluorescent positive CD4 T cells coming into the genital tract at the different days after infection. And the black line here is the bona fide Th1 T cells that do not express yellow fluorescent protein. And what we can see here is that they're able to come into the genital tract and respond towards infection by expansion. And then around day 7 and between day 7 and day 14, the infection is cleared in the vaccinated mice, and then they're able to retract. However, they actually stay there as tissue-resident cells, even though that it's 57 days after infection, and there's no active infection going on. So this was really interesting, and we really wanted to look further into what kind of cells these YFP positive cells were. So we divided the cells according to their expression of YFP, IL-17 expression, and also Th1 cytokines, which I defined as interferon gamma, IL-2, and TNF-alpha. And what we see here is that within the Th17 derived cells population, we find classical Th17 T cells, we find Th1 T cells that have lost expression of IL-17, and then we have this undefined population which do not express IL-17 or any of the 3 other cytokines that we looked at. So we couldn't really define what this population was. We just knew that it came from Th17 T cells. So we became a bit more curious about this population. So we wanted to characterize them further. And that's why we used a single cell RNA sequencing approach, where we looked at the Th17 T cells at day 11 in the genital tract of the vaccinated mice, and also after infection. We did the same setup to get a hold of the vaccine-specific CD4 T cells, and then we sorted the cells by flow cytometry. And then we used the BD Rhapsody system to perform whole transcriptome and VDJ sequencing to look at the TCR clonotypes. So what I've shown here are all the cells. The smaller dots are all cells. This is a UMAP projection of the 2,000 most variable genes among the Th17 derived cells, which were the yellow YFP positive, CD4 high, and CD4 positive cells. We used the top 10 cluster markers together with lineage markers to define the different cell types that were enriched in the clusters. As you can see here, we defined this cluster as more stem-like, enriched in stem-like genes. And these stem-like T cells are defined by being very persistent and also being able to have a higher proliferative capacity and being able to differentiate it towards different kind of CD4 T cells. Then we have a cluster here, which is enriched in type 1 interferon-stimulated genes. We have a effector subset here, which is defined by classical Th17 genes. Then we have a mixed effector T helper cluster, which include both Th1, and majority of it, and Th2, and also follicular helper cells and cytotoxic T cells also. And then we have this intermediate T helper subsets, which express the similar genes to the effector subsets, but just into a lower degree. So we became very curious about the relationship between the different subsets, especially having a more memory subset and having a more effector subset here. So we wanted to dissect their relationship even further. So what we did here is that we did RNA velocity. And the principle of RNA velocity is it uses intron and extron regions to determine the amount of unspliced and spliced mRNA. So the basic principle is that if you have cells expressing a lot of immature mRNA for a pool of genes and another cluster expressing the same genes but in a mature form, there's likely a transition going from these cells to the other cells. So this is the principle of RNA velocity. And what I show here in the first UMAP plot, all the arrows show the different velocity values going from one subset to another. And the arrows in the direction show that some of the cells here actually transition, or it suggests that it transitioned into the cells that are found in the other clusters. So from cluster 2, which were the more memory stem-like cluster, we see that they've transitioned into cluster 1 and also cluster 0, and from there to the effector clusters. Using this information, the algorithm also ordered the cells in a differentiation timeline and then plot them in this pseudotime. And what you can see here is that the stem-like clusters, the cells within are ordered very early on, whereas the effector subsets, which are found here and here, are ordered very late on. Suggesting that there is a differentiation going on and that these cells that were stem-like, they will come earlier than the effector cells or developed earlier. So it suggests that there's a shared developmental pathway for the Th17 derived cells. So this we wanted to confirm further. So we did TCR analysis to see if the Th17 T cells actually share origin. At this point, we're not quite sure about that. So what I did here and what I can show you here is all the different clusters with the same colors. We see different circles, which are the clonotypes within the clusters. And the size of the circles determines how many clonotypes of the same clonotype is found within the cluster. So if you look at the top 6 TCR clonotypes, we see that all of the subsets actually include these top 6 expanded clonotypes, meaning that they all expand and that they actually share the same TCR clonotypes, meaning that they have a shared origin. So what I conclude from all this is that the Th17 T cells give rise to different distinct subsets with distinct immunophenotypes. They share a developmental pathway and they also share origin. So we see that they give rise to these different effector subsets, and we became curious about what role they played for protection. So we asked ourselves how we see that the Th17 T cells give rise to Th1-like cells. So we asked ourselves how important the Th1 response were for protection. So by looking using a TBET knockout mice, we could see the contribution to protection from both Th1, bona fide Th1 and also Th17 derived Th1 against protection against chlamydia. So we looked after infection, and what we see here is that when we vaccinate a TBET knockout mice and compare them to an unvaccinated TBET knockout mice, we see that the vaccinated group is still able to reduce the level of bacteria even without a Th1, and it reduces the bacterial level to the same degree as we have observed in wild type mice. So even though they do not express any Th1, we were still able to control infection at this point. Then if we looked at the recruitment, we saw that this correlated with CD4 T cells still coming into the genital tract. They express IL-17 and TNF-alpha and IL-2, and also all three of them on the same cells. However, do not express any interferon gamma. So we see that there's still still protection observed despite the lack of bona fide Th1 and Th17 or Th17 derived Th1 T cells. So we asked ourselves, okay, maybe it's the other effector subset that is important, and asked ourselves if the IL-17 signaling from the Th17 T cells contribute to protection. So what we did is that we used a antibody that blocked IL-17 signaling during infection, and we also established that Th17 T cells are the main source of IL-17 during infection. So we blocked, and then we looked at protection. And what we can see here is that we have two vaccinated groups, the red and the blue, and this group were treated with the blocking antibody against IL-17, and we saw that when we block IL-17 signaling, we actually see an increase in bacterial numbers to the same degree as the non-vaccinated mice group we see here. So we see that when we block IL-17 signaling throughout infection, this results in a loss of infection control. This correlated with both a decrease in neutrophils, seen here, and more remarkably at day 7, and also a decrease in Th1 recruitment and Th17 recruitment here by looking at the cytokine expression. So what we can conclude here is that blocking of IL-17 signaling during infection results in a loss of infection control. So the overall conclusion from this study is that CAF01 induced these plastic Th17 T cells that give rise to distinct subsets. They share a development and can possibly give rise to one another. They share TCR specificity. And we really want to investigate the role of the other subsets further, especially this stem-like subset, to see if they actually give rise to the other effector subsets. Looking into the major effector subsets, Th1 and Th17 T cell subsets, we can see that early control of infection was still observed despite lacking TBET and interferon gamma expressing cells. And then we also saw that IL-17 signaling from the Th17 T cells are important for vaccine-mediated control of infection. So what we can conclude from this about the role of Th17 T cell is that the Th17 T cells contribute to the vaccine-mediated response by giving rise to several distinct functional subsets, including this protective IL-17 producing subsets. Yes, so I just wanted to say thank you to my colleagues and all our collaborators and the funding that made all this possible. And then thank you all for listening to me, and I will be happy to take your questions.
Thank you so much, Nina. This was an extremely interesting topic. I think we are all very much interested in the characterization of Th17 at in this moment, especially. So we are running a bit late, so I suggest we take 2 questions per speaker. So please don't hesitate to write them in the Q&A. And then if you have extra questions. If you want to contact them, what is your preferred way of being in contact? In case you can share it. So
I have my email in the corner here, or I can also be found on LinkedIn.
So we can ask the first question to Dennis. So is it advantageous to use adjuvants that stimulate two PRRs in the same cells over a single binding PRR, or does it overstimulate the cells and have potentially adverse effects?
Well, again, it's not a simple question. In some cases, it's really good with synergy. In some cases, you don't see any effect. In some cases, you can also induce reverse effects and inhibit responses. I think for definitely going back to the CAF9 system where we have an immune, we have a MMG as a C-type lectin receptor agonist targeting MINGLE combined with poly-IC that induces that targets TLR3. We definitely see a synergy with those two. In other cases, we haven't seen much synergy and much added value to it. I think you have other examples where there seems to be some degree of synergy, but you might have to look for it. You have the AS01 system, for example, for designed by GSK, where you have QS21 and MPL. If you just look at the short-term responses, you might not need MPL, but actually you see that on the memory, on the long-term memory, it has some effects to it. So they definitely, you can see areas where you see a synergy, but in other cases you won't. I think on the question about too much activation, that's a dosing issue. You can always balance that out. Unfortunately, you probably have to do that in vivo, because in vitro you always have too much responses because you expose so hardly. But yeah.
Thank you so much for the answer. And by the way, thank you for answering to the other questions. So if you go on the Q&A and answer, you can see the responses to some of the questions before that Dennis wrote. So I have a question for Nina now. How is the antibody response affected in the TBET knockout mice, and what effect does this have on the protection from infection?
Yes, yeah. So I didn't share the antibody responses, but what I can say is that it is not affected in the TBET knockout mice. We still see the same IgG subclasses showing up as we saw in the wild type mice. So therefore, we concluded that it didn't have there wasn't any contribution from the antibody on the protection in this study. And what I can say about the general role of antibody with our vaccine is that we see in animal models that antibodies do play a role in the early infection. So especially in the vagina, where the bacteria first meets the host, their antibodies play a major role. But if the bacteria is able to ascend into the upper genital tract, we need CD4 T cells. We need the Th1 and Th17 T cells to protect against infection and control the infection.
Thank you so much for the question. So next one, I will still ask a question to Dennis. So you talked about the no one solution fits all in vaccine adjuvant development. So how does this principle apply to the design of CAF adjuvants?
Well, I think that the CAF adjuvant, the platform of CAF adjuvants, may apply to the not a one solution fits all. It's rather the other way around. I think it's what I meant with not a one solution fits all is that there's each pathogen demands different reactions from the immune system to be optimally defeated. And therefore you need to generate different immune fingerprints, different flavors of immunity to best protect against infection. Extremes are, of course, where with influenza you need very high neutralizing antibodies. If they're effective enough neutralizing antibodies, they are also good to fight the infection. Where with TB, antibodies basically do not play a role or a very minimal role, basically due to the way they infect. And therefore you need different immune fingerprints, and thereby you need different adjuvants to induce those immune fingerprints. And this is where by adding different immune stimulators into your adjuvant or into your vaccine, you can change the flavor to fit what is needed. And that was what I meant with not a one solution. We will never get a one adjuvant that fits all vaccines. It also depends on the selection of antigens. Well, for pneumococcus, for example, yeah, you have there are new generation and vaccines where they are focusing a lot on the T-cell responses, but actually those that are existing right now, they are solely based on antibody responses, and they would need different support in delivery and immune stimulation to support that. So even within the same pathogen, you can select antigens that are solely focusing on one immune response. So therefore you need to select your adjuvant according to know your correlates of protection. That's always nice. And if you don't know it, use adjuvants to find out, because you can just take a plethora of different adjuvants and see which one protects the best.
Yes, thank you very much. So I will ask last question to Nina, and then I think we can close. So we were curious about other administration routes for and the benefits that different administration routes could have in inducing Th17 response. So have you investigated this in any ways?
Yes, so we have a study on using, or where we looked at what role the having tissue-resident memory T cells already there, what role that played in protecting against chlamydia. So we did like a proof of concept study where we induced Th1 and Th17 and also IgA in the genital tract by intrauterine administration together with subcutaneous administration. And what we saw is that the tissue, having tissue-resident memory T cells there and IgA actually gave superior protection. But however, that strategy wouldn't be that favorable to do in real life. And we also saw that it gives superior protection, but it's not necessary for protection. But we've also looked into some studies done before my time have looked into giving it intranasally, which is also a good site to prime Th17 response, and then also saw that there is some cross-tissue immunity between the nose and the genital tract, thereby creating this local immunity by priming in the nose.
Thank you very much. So that was great. So I think we can close here. We are over. Yeah.
I have one. I didn't comment on how to contact me. My email was also on the presentation, and of course you can reach out on LinkedIn also.
So anyways, this has been recorded, as I told you, so it will be on YouTube. So if you want to follow it again and check again for the email, it's gonna be there in a few days. So thank you very much to both. Those were great presentations. We learned a lot today. I think everyone can agree. And yeah, thank you again for from all the ISV committee and also from the attendees for sure, even though they cannot talk. So next webinar will be on July 10th, and it's going to be a more specifically career webinar. We will have Ravi Degun from Ernst Young and also Martin Rabel from Citiva, that they will talk to us about their career journey. So write it on your agenda. Thank you, and bye-bye. Have a
Bye.
nice day.
Bye.
You too.
Bye-bye.